Question 3b. Compounds of SO2, sulfur dioxide, and magnesium oxide both contain oxygen. The table below shows the melting point of both of those compounds. Predict this type of structure and bonding of SO2 and MgO and explain their difference in their melting points. So, if we look at the melting points, first thing to note, the melting points have been given in Kelvin. So just be aware of that, because that could be misleading. If you don't realise what's going on, think of that as 200 degrees C, you could be misled. So 200 Kelvin as opposed to 3,125 Kelvin. So what we've got here is a low melting point, and obviously then a very high melting point here. So direct comparisons, we know straight away if it's a low melting and boiling point, we only are going to be overcoming intermolecular forces. So SO2 is going to be a simple covalent structure, whereas magnesium oxide, metal, non-metal, two ions joined together, very high melting and boiling point. That's telling me that magnesium oxide is a giant ionic lattice. So let's start off with predicting the structure and bonding. So SO2, we've got simple covalent lattice because the melting point and boiling point is so low. And we've got MgO, which is going to be a giant ionic lattice. Remember to refer to it in its entirety. Don't just say ionic structure or ionic lattice. Make sure you make reference to the word giant. That's got to be in there. And that's in fact 1 mark each for both of those structures. So simple covalent is 1 mark, giant ionic is a 2nd mark. Now we're looking to explain the difference in their melting points. So as I've said before, melting and boiling points are always related to the strength of the attractions between the particles. So either the intermolecular forces or the bonds that are present there in the first place. So with SO2, as it's a simple covalent molecule, when you melt or boil it, all you're trying to do is break or overcome the intermolecular forces. With MgO as an ionic lattice, a giant ionic lattice, you would need to break the ionic bond. So the reason why the melting point is so much higher is we can say here that the ionic bond in magnesium oxide is much stronger than the intermolecular forces in SO2. Okay, you could say London forces, you could say permanent dipoles, you could say induced dipoles. They're not going to be hydrogen bonds, obviously, because there aren't any hydrogens there, so you can't say hydrogen bonds. But in this case, because it's not specifying what you've got, you could say just in general intermolecular forces. Okay, but the interactions here would probably be London forces. So a statement there saying that the ionic bonding is going to be a lot stronger than the intermolecular forces in SO2 will get you another mark. So there's 1, 2, 3. And as always, as I've said before, and the idea behind this booklet is the repetition, so this sticks in your mind. When you're talking about that, your answer should always come back to energy. So if the ionic bonding is stronger, then more energy is needed to break the ionic bond. Okay, than the intermolecular forces, but you're inferring that by saying that it's stronger. All right, but you must make sure you bring that argument all the way round to the idea of energy needed to overcome or break the forces or bonds.